Good day and welcome to this discussion on section 5.5, which is on double integrals in polar coordinates. So let's first talk about polar coordinates. As you know, any point in the Cartesian plane can uniquely be represented by an ordered pair of real numbers. Let's take as an example the ordered pair of numbers 4, 3. There is only one point in the Cartesian plane that we can use to represent this point, namely the point where x is equal to 4 and y equals to 3. The converse, of course, is also true. If you take any point in the Cartesian plane, you can find a unique pair of ordered numbers that represents that point. There is another unique way of representing a point in the Cartesian plane. We start off by measuring the distance, let's call it r, from the point P to the origin. This is obviously a fixed number. Next, we also measure the angle, which we call theta, that is formed between the line segment joining P to the origin, the line segment OP, and the positive side of the x-axis. That is also a fixed number. So we can say that the ordered pair r, theta is a unique representation of the point P. Using our knowledge of the trigonometric functions, we can easily see what the relationship is between the Cartesian coordinates of a point and the polar coordinates of a point. It is clear that x must be equal to r cos theta and y must be equal to r sine of theta. Note that r can never be negative because it's a distance. In the example above, the angle theta is positive and is measured anti-clockwise. For a point in the fourth quadrant, however, the angle theta will be measured clockwise and will be negative. Let's look at an example to demonstrate that. In example 1, we must describe a region that's given in Cartesian format in polar coordinates. As you can see, the region D is a semicircle. It is the right-hand side of a circle with center at the origin and a radius of 2 units. If r, theta is the polar coordinates of a point in D, it is clear that r must lie between 0 and 2. This is because the distance from any point in D to the origin cannot be greater than 2. If the point lies in the first quadrant, theta will be positive, and it is clear that it will lie between 0 and pi over 2. On the other hand, if the point is in the fourth quadrant, we will be measuring theta clockwise. Theta will be negative, and hence it will be between negative pi over 2 and 0. We can now describe D by saying it's all points of the form r, theta, where theta lies between negative pi over 2 and pi over 2, and r lies between 0 and 2. So why do we want to use polar coordinates at all? I'm sure that you will agree that in the previous example, the polar description of the region was much more elegant than the Cartesian description. Also, as you will see in some of the examples we'll do a bit later, some integrals that are almost impossible to calculate in the Cartesian form can easily be calculated if we transform them into polar coordinate form. The question is, how do we go about changing from the Cartesian coordinates for an integral to the polar coordinates? Well, we've got a very nice theorem that tells us exactly how to do that. Let's check the conditions of theorem 154. You will notice that the first thing that is required is that you need a function f that is defined on a region S in the xy plane, and that needs to be a continuous function. Secondly, you need to have a region S in the xy plane that can be described in polar coordinates. The theorem tells you that this region S in the xy plane will be transformed to a region R in the r theta plane. Finally, the theorem gives you a formula to transform the double integral over S to a double integral over R. One very important thing that you must notice is that there is an R added to the integrand on the right-hand side. The factor R is called the Jacobian of the transformation, and we'll talk more about that when we do section 5.6. You can almost see the Jacobian as the price that you pay for the transformation that you are making. It is important to note that while Theorem 154 is formulated in terms of rectangular regions, the same result also applies to more general regions, like the type 1 and type 2 regions that we discussed previously. Let's do an example where we apply this theorem. You may recognize this example. Dr. Wiggins actually discussed this in one of his previous lectures. You will remember that he did not conclude the final integral and said that we would return to this later on. Well, now is the time. If you go back to that example, which was example 147, you will see that we arrived at the formula for the volume as being the double integral over d of that expression, where d is the region inside the circle x squared plus y squared equals 1. Since the region D is simply a unit circle, it's clear that we can describe D in polar coordinates by the inequalities theta between 0 and 2 pi and r between 0 and 1. To use a transformation to polar coordinates, we know that we must equate x equal to r cos theta and y equals to r sin theta. That means that x squared plus y squared is r squared. So the expression that we need to integrate, namely 2 minus x squared minus y squared in brackets, minus the root of x squared plus y squared, just becomes 2 minus r squared minus r. We now apply Theorem 154, and we can see that the volume is given by the double integral 0 to 2 pi, 0 to 1 of 2 minus r squared minus r times r dr d theta. Again, you must notice that we've added the Jacobian, which is r. We can now go ahead and do the double integral, and you can check the calculations there. The final answer is 5 pi over 6. Let's have a look at another example. Let us first have a look at the region D that is given. The region D is in the first quadrant, inside the circle with radius 2 and center at the origin, and above the line y equals x. I hope you can clearly see that that is the area shaded in green. That is our region D. Now let's talk about the integral itself. You can probably see that with the knowledge you have so far, you've got no idea how to integrate cos of x squared plus y squared if that's all that is given. We're going to show you that if we transform to polar coordinates, we can actually evaluate this integral. We begin by describing the region D in polar coordinates. You can see that theta must lie between pi over 4 and pi over 2, and the maximum value of the radius r can obviously only be 2. Again, remember that our transformation is given by x equals r cos theta and y equals r sin theta, which implies that x squared plus y squared is r squared, and so the expression cos of x squared plus y squared just becomes cos of r squared. We now use Theorem 154 to find a double integral in terms of r and theta. Note that we have added the Jacobian r. We can now calculate the double integral. You can check the calculations, and as you can see, the final answer is pi over 4 times sine of 4. Let's do one more example. In this example, we actually know what the answer should be, but it is a very useful example to demonstrate the use of polar coordinates. We are instructed to use polar coordinates to find the area of a circle that basically has a radius of 2. We know how to calculate the area of a circle with radius 2, and we know that the answer will just be 4 pi. Now let us describe this circle in terms of polar coordinates. It's clear that theta will start at 0, that is the positive side of the x-axis, and will move anti-clockwise all around to the negative side of the x-axis. That means the maximum value of theta will be pi. The range for r is a bit more complicated. R will range from 0 to the edge of the circle. We now need to describe the circle in polar coordinates using our normal transformation, x equals r cos theta and y equals r sin theta. As you can see, we come to the conclusion that the equation of that circle is r equals 4 sin theta for r not equal to 0. That means that the range for r is between 0 and 4 sin theta. We can now find the area as the double integral over d of 1 dA, which we then convert to a double integral with polar coordinates from 0 to pi, 0 to 4 sin theta, and remember the Jacobian r. You can check the rest of those calculations, and let's have a look at the final steps. To integrate sine squared of theta, we use the trigonometric identity. Sine squared of theta is a half of, in brackets, 1 minus cos 2 theta, and then the integration is not complicated. The final answer is 4 pi, as we knew right from the beginning. That concludes the examples that we will be doing in this video. There are many more very good examples in the course notes, and I strongly recommend that you work through those examples and also work on the exercises. That concludes this video. Goodbye and good luck.